13.8 billion years. That was the age of everything. Written in textbooks, confirmed by satellites, accepted as finished science. Then, a telescope the size of a tennis court unfolded 1 million miles from Earth, pointed at the oldest dark, and started sending back something wrong. Galaxies, massive and chemically mature, fully formed less than 300 million years after the Big Bang. Physics said there was no time for them. We will explore those impossible galaxies, the physicist claiming the universe is actually 26 billion years old. The Nobel laureate who says our Big Bang was a transition, and a century-old theory making its comeback. If this changes everything for you, subscribe. Prepare yourselves. We begin. For most of the 20th century, the age of the universe was not a question. It was an answer. 13.8 billion years. You learned it in school. Physicists wrote it into textbooks. Governments funded satellites to confirm it. By 2018, the European Space Agency's Planck satellite had delivered what the scientific community called the final word. The announcement landed with the quiet confidence of a case being closed. Here is how they arrived at that number. In every direction you look, there is a faint glow left over from the earliest moments of the cosmos. It was released roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen for the first time. Before that moment, the cosmos was a hot, dense plasma, and light could not travel freely through it. After it, the universe became transparent, and that first freed light has been traveling toward us ever since. Scientists call it the cosmic microwave background. It is not perfectly uniform. Tiny temperature differences, no larger than 1 part in 100,000, ripple across the entire sky. These fluctuations are not random noise. They are the fingerprints of pressure waves that moved through the early universe's hot plasma, patterns so precise that physicists can extract the full composition of the cosmos from them. The density of ordinary matter, the density of dark matter, the geometry of space, the expansion rate, all of it encoded in a glow older than any star. The Planck satellite mapped this ancient light with extraordinary precision. 35 distinct peaks in the data, each consistent with the model. The age came out to 13.787 billion years, give or take 20 million. The uncertainty was smaller than a rounding error in geologic time. Cosmologists shook hands. The question was settled. The standard framework, a model built on dark energy and cold dark matter, had delivered its verdict, and the universe had agreed. This was the kind of certainty that entire careers are built on, the kind that stops conversations before they begin. But beneath that confidence, something was already wrong. To calculate the age of the universe, physicists need to know how fast it is expanding today. The Planck measurement gave one answer: 67 kilometers per second for every 3.25 million light-years of space. But other teams, measuring the same expansion rate using a completely different method, tracking pulsating stars and exploding stars in nearby galaxies rather than the ancient glow, kept arriving at a different value: 73, not 67. The discrepancy was 5 standard deviations wide. In physics, 5 standard deviations is when you stop calling something a coincidence. A higher expansion rate means the universe expanded faster and reached its current size in less time. Under that local measurement, the universe would be only 12.9 billion years old. Under the Planck measurement, it would be 13.8, one universe, 2 methods, 2 incompatible answers. Physicists named this the Hubble tension and spent years arguing about which ruler was broken. Neither side could prove the other wrong. The crack in the foundation appeared before any new telescope had been launched, before anyone had stared deeper into the dark. Nobody knew yet how wide that crack was about to become. It took 25 years to build. The James Webb Space Telescope was conceived in the 1990s, delayed for decades by budget overruns, redesigns, and a near cancellation that nearly ended it before the mirrors were ever polished. $10 billion. 1 million miles from Earth, parked at a gravitational equilibrium point where it would never drift into our planet's shadow and could keep its infrared detectors cooled to temperatures approaching -448 degrees Fahrenheit. The engineering required to get it there was so complex that a single misfolded panel during launch would have destroyed the most expensive scientific instrument humanity had ever attempted to build. It launched on Christmas Day, 2021. The world watched as it unfolded in space like an origami flower, one segment at a time. The James Webb Space Telescope was designed with a specific mission in mind. Astronomers called it cosmic dawn, the period roughly 200 to 400 million years after the Big Bang, when the very first galaxies were switching on. Light from those galaxies has been traveling for so long that the expansion of the universe has stretched it far beyond what human eyes can see, shifting it from visible wavelengths deep into the infrared. Webb's golden mirrors were tuned precisely to catch that stretched ancient light. The scientific community had strong predictions about what it would find. In the standard model, the early universe should look like a construction site. Small, dim, clumpy structures pulling together under gravity. Proto-galaxies in their infant stages. Irregular, chaotic, sparse. The theoretical models were clear. The universe was too young and too undeveloped in that epoch to have produced anything large, ordered, or chemically complex. Webb was expected to confirm this picture, to see the building blocks of galaxies before they had finished assembling. The first images arrived in the summer of 2022. The public release was a celebration, stunning deep-field photographs, thousands of galaxies visible in a patch of sky no wider than a grain of sand held at arm's length. And then, quietly, the astronomers started looking at the data. What they found in the early release images was not what the models had predicted. Webb's cameras were picking up light from objects far more distant than expected, far more massive, far more structured. They were not seeing a construction site. They were seeing something that looked, in some cases, like a finished building. The conference calls started. The emails went out. Researchers who had spent their careers building the theoretical framework for early galaxy formation began comparing notes, each one arriving at the same uncomfortable realization. These objects existed at cosmic distances that the standard model said were simply too early for anything like this to have formed. Nobody announced it publicly right away. Scientists are careful. Scientists check their work. But in the months that followed, the spectroscopes were pointed, the redshifts confirmed, the masses calculated, and the more carefully the data was analyzed, the more clearly the problem came into focus. Something was out there that should not exist, and figuring out why it was there would require dismantling assumptions that the field had spent 50 years treating as certainties. The first candidates arrived quietly, flagged by software algorithms scanning Webb's earliest deep-field images. Red, distant, enormous, galaxies sitting at redshifts of 10, 11, 12, and beyond, which translated to look-back times so extreme that these objects existed when the universe was supposedly only a few 100 million years old. In the standard model, the universe at redshift 10 was less than 500 million years old. At redshift 12, less than 400 million. These galaxies had no business being as large as the data said they were. Then came the confirmation that stopped the field in its tracks. In May of 2024, an international collaboration announced the spectroscopic confirmation of a galaxy designated JADES GSZ140. A spectroscopic confirmation means there is no ambiguity. The redshift is not an estimate from color, it is a direct measurement from the fingerprints of specific elements in the galaxy's light. The number came back at 14.32. The galaxy existed just 290 million years after the Big Bang. 290 million years. To put that in perspective, the Earth itself is 4.5 billion years old, 15 times longer than this entire galaxy had to form. And yet there it was, not a wisp of gas beginning to collapse. a fully fledged galaxy, already hundreds of millions of times the mass of our star system, already producing light so bright it ranked among the most luminous known objects at its distance, already organized enough to be forming stars at a rapid rate. Here is where it gets stranger. The astronomers measured the spectrum carefully, looking for what elements were present, and they found oxygen. Oxygen is not a primordial element. The Big Bang produced hydrogen and helium. Oxygen is forged in the cores of massive stars through nuclear fusion and then scattered across space when those stars explode as supernovae. For oxygen to be present in a galaxy seen 290 million years after the Big Bang, entire generations of massive stars had to be born, live their short, intense lives, and die in spectacular explosions, all before the observation. Star formation had to have begun at least 100 million years earlier still. That pushes the required start of star formation in this galaxy back to nearly the very moment the Standard Model says the universe first became transparent to light. Then came a second galaxy, JADES GS-Z140's neighbor, designated Z14-1, confirmed at redshift 13.9, and alongside these two, a catalogue of candidates at extreme distances was building rapidly. 6 massive red galaxies at redshifts between 7 and 9, some with stellar masses approaching 100 billion times the mass of our star, announced in early 2023. Galaxies appearing to have already retired from star formation before the universe was supposedly old enough to have produced a single mature galaxy. Each new discovery sharpened the same question. The models said there was not enough time for these objects to exist. The observations said they existed anyway. Something had to give. Either the observations were wrong, or the models were, and the observations were spectroscopically confirmed. The math was about to break in a way nobody had anticipated. Numbers are supposed to be reliable. That is the whole point. When astronomers observed these extreme early galaxies, the first thing they did was the calculation every physicist does: run the math. How much time did the Standard Model allow for galaxy formation at redshift 14? How much mass could physically accumulate in that time? What star formation rate would be required to produce what Webb was seeing? The calculation was not complicated. At redshift 14.32, the Standard Model placed the universe at 290 million years old. To produce a galaxy with hundreds of millions of stellar masses in that window, you would need to convert gas into stars at a rate approaching 100% efficiency. 100% efficiency. Every atom of available gas turning into a star with no waste, no feedback, no energy blasting outward from newly formed stars to disrupt the surrounding gas clouds. In real astrophysics, star formation is a messy, inefficient process. Galaxies in the local universe convert only a few % of their available gas into stars in any given period. The most extreme star-forming galaxies known push toward 30 or 40% briefly under exceptional circumstances. 100% is physically impossible. Stars form in cold, dense clouds of gas. Those clouds must first cool from the hot diffuse plasma of the early universe. Gravity must slowly pull the gas together. Turbulence resists collapse. Once stars ignite, their radiation and winds push the surrounding gas outward, often shutting down further star formation entirely. None of these steps can be skipped. All of them take time. Michael Boylan-Colchin, a cosmologist at the University of Texas at Austin, published a direct analysis of the problem in the journal Nature Astronomy in 2023. His conclusion was unambiguous. These galaxies sit at the very edge of what the Standard Model permits, and in some cases, beyond it entirely. The universe, as the model describes it, simply did not have enough runway for what Webb was photographing. Other researchers attempted patches. Perhaps the very first stars were behaving differently, burning hotter and faster than the stars we see today. Perhaps black holes in the infant universe were growing explosively and seeding galaxy formation earlier than expected. Perhaps feedback mechanisms were somehow suppressed in the early cosmos. allowing gas to collapse more efficiently. Each proposed fix strained further against observation. And then, a different kind of question began circulating in papers and conference talks, cautiously at first, then with increasing urgency. The question was this: what if the calculation was based on a flawed assumption? The age of the universe at redshift 14 is not something we measure directly. It is something we derive from our model of how the universe expanded. If the model is wrong, the ages are wrong. If the ages are wrong, the timeline is wrong. If the timeline is wrong, those galaxies are not impossible at all. They simply lived in a universe that had more time than we thought. The idea was uncomfortable. It required questioning a foundation that the Planck satellite had seemed to confirm with extraordinary precision. But the galaxies were there, the oxygen was there, the math was broken, and the alternatives were stranger than anyone expected. In 1929, the same year, Edwin Hubble published the law that would reshape cosmology. A Swiss-Bulgarian astronomer named Fritz Zwicky proposed something that the scientific community spent the next century trying to forget. Zwicky was watching the light from distant galaxies grow redder with distance, the same observation Hubble was making. Hubble interpreted this reddening as evidence that the universe is expanding, carrying the galaxies away from us like marks on the surface of a balloon being inflated. The farther a galaxy sits, the faster it recedes, and the more its light is stretched toward the red end of the spectrum. Zwicky looked at the same data and asked whether there was another explanation. What if the universe is not expanding? What if light simply grows tired as it travels? A photon crossing billions of light-years of space might gradually lose energy along the way. Lower energy means longer wavelength. Longer wavelength means redder color. In Zwicky's model, distant galaxies appear redder not because space is stretching between us, but because their light has been slowly draining of energy during the journey. He called it tired light. The idea was dismissed almost immediately. The most obvious problem was image quality. If photons were scattering or interacting with matter as they lost energy, those interactions should blur the images of distant galaxies, smearing their shapes into indistinct fuzz. Distant galaxies remained sharp. The argument seemed decisive. Then there was the cosmic microwave background, discovered in 1965. Its thermal spectrum was an almost perfect blackbody curve, the specific signature of light that has been in thermal equilibrium with matter. In a static, tired light universe, producing that precise curve is extraordinarily difficult to explain. In an expanding universe, it falls out naturally from the physics of the early hot plasma. By the 1980s, tired light was considered a historical curiosity, the kind of wrong idea that physicists mention in footnotes and then move on from. Zwicky had long since died, in 1974, without seeing his idea revisited seriously. But Zwicky had a habit that was easy to overlook. He had a habit of being right about the things the field dismissed. In 1933, he examined the Coma galaxy cluster and noticed something strange. The galaxies within it were moving too fast for their visible mass. The gravity produced by the stars and gas he could see was nowhere near enough to hold the cluster together. Something invisible was providing additional gravitational pull. Zwicky proposed that clusters contain vast quantities of unseen matter and gave it a name: dark matter. The scientific community ignored him for 40 years. Then, in the 1970s, Vera Rubin and Kent Ford found the same discrepancy in galaxy rotation curves, and the concept was finally accepted. Dark matter is now a cornerstone of the Standard Model. The man who discovered dark matter and proposed tired light. One idea vindicated after 4 decades of silence. The other idea still waiting. In 2023, with galaxies appearing in Webb's images that the standard timeline cannot explain, a retired professor in Canada decided it was time to dust off Zwicky's second idea. What he found would shake the field in ways nobody predicted. Rajendra Gupta spent most of his career in relative obscurity. A physicist at the University of Ottawa, retired from active teaching, still working from his office, still publishing. In 2023, he submitted a paper to the monthly notices of the Royal Astronomical Society. The journal accepted it. The claim inside was audacious enough to stop scientists mid-sentence when they read it. The universe is not 13.8 billion years old. It is 26.7 billion years old, nearly double. The paper was not a thought experiment or a philosophical argument. It was a mathematical model fitted against real observational data, including the same supernova measurements that underpin the standard timeline. Gupta called it the covariant coupling constants plus tired light model, two ideas working together. The first comes from a proposal made by the physicist Paul Dirac in the 1930s. Dirac noticed that certain ratios of fundamental constants in physics, large dimensionless numbers like the ratio of electrical force to gravitational force between two protons, are suspiciously similar in magnitude to the age of the universe expressed in atomic units. He suggested this might not be coincidence. The constants, Dirac speculated, might not be constant at all. They might be slowly evolving as the universe ages, their values drifting as space expands. Gupta built this idea into a rigorous mathematical framework, allowing the strength of electromagnetic, gravitational, and nuclear forces to vary over cosmic time. The second idea is Fritz Zwicky's tired light, a partial contribution to redshift from photon energy loss during travel, separate from the stretching caused by expansion. Gupta did not replace expansion with tired light. He added a tired light component alongside expansion, a hybrid in which both mechanisms share the work of reddening distant light. The result of combining these two effects is dramatic. At redshift 10, in the standard model, the universe is roughly 500 million years old. In Gupta's model, the same redshift corresponds to an age of 5.8 billion years, more than 10 times longer. At redshift 20, the standard model gives 180 million years. Gupta's model gives 3.5 billion. The impossible galaxies dissolve as a problem immediately. 5.8 billion years at redshift 10 is more than enough time for massive, chemically enriched galaxies to form through ordinary physics. No exotic patches required. No star formation efficiencies exceeding 100%. The galaxies had time because, in this model, they always had time. We were simply miscounting. The implications did not stop there. In a follow-up paper published in the Astrophysical Journal in 2024, Gupta extended the model further. If the coupling constants of nature are changing as the universe expands, the force laws governing galaxy dynamics are changing too. The rotational speeds of galaxies, which in the standard model require vast halos of invisible dark matter to explain, fall naturally out of the modified force laws. No dark matter needed. Dark energy, the mysterious repulsive force supposedly accelerating cosmic expansion, also vanishes. The apparent acceleration is reinterpreted as the natural effect of weakening forces across cosmic time, not a new substance filling the vacuum of space. One paper, one retired professor, two of the central pillars of modern cosmology called into question, and the establishment was not happy. Imagine erasing every timeline you were ever given about the universe and replacing it with one that is twice as long. At first glance, doubling the age of the universe sounds like a small revision, a correction at the margins. In practice, it rewrites nearly everything. Start with the first stars. In the standard model, the very first generation of stars formed somewhere between 100 and 200 million years after the Big Bang. These were enormous hydrogen and helium stars with no heavy elements, burning ferociously bright and dying in violent explosions that seeded space with the first traces of carbon, oxygen, and iron. In the standard model, this entire cycle had to happen within an impossibly compressed window before the massive galaxies Webb observed at redshift 14 could have accumulated their chemical richness. In a 26.7 billion year universe, at redshift 20, the cosmos is already 3.5 billion years old. 3.5 billion years for the first stellar generation to form, live out their brief violent lives, explode, and scatter their metals across surrounding gas clouds. 3.5 billion years for the next generation to ignite from that enriched material. 3.5 billion years of stellar recycling before the galaxy's web observed at redshift 14 even appear in our images. The oxygen in JADESGSC 140 becomes unremarkable. Of course, there is oxygen. In this timeline, the universe has been doing chemistry for billions of years already. The quenched galaxies, the ones Webb found that had already stopped forming stars before the universe was supposedly a billion years old, stop being puzzling too. Galaxies retire after they exhaust their supply of cold gas. That process takes time. In the standard model, there was not enough time. In Gupta's model, galaxies at redshift 5 or 6 have had billions of years to work through their gas supplies and go quiet. They are simply old. The spiral galaxies Webb discovered at redshift 6, with their graceful arms and organized disk structures, had always been the deepest mystery. Spiral structure requires orbital dynamics to settle and persist over many galactic rotations. Each rotation takes hundreds of millions of years. In the standard model, the universe at redshift 6 was less than a billion years old, not enough time for a galaxy to have completed enough orbits to develop spiral arms. In Gupta's model, the universe at redshift 6 is roughly 5 billion years old. Spirals are not just possible, they are expected. Then consider what the model does to dark energy. The cosmological constant, the term Einstein, added to his equations, and then called his greatest mistake, currently serves as the mathematical representation of dark energy. It is the engine supposedly driving the accelerating expansion of the universe. In Gupta's framework, that acceleration is a misreading of the data. The universe appears to be accelerating its expansion because the forces governing its behavior are weakening over time, not because some invisible energy is pushing space apart. Dark energy, in this model, is a phantom, an artifact of applying constant force equations to a cosmos whose forces are slowly fading. The impossible galaxies, the retired galaxies, the spiral galaxies, the missing dark matter, the mysterious dark energy. One model dissolves them all. Whether the model is correct is a different question entirely. But the next challenge to the standard timeline came from an entirely unexpected direction, and it came from a Nobel laureate. Roger Penrose received the Nobel Prize in Physics in 2020 for proving that black holes are a direct consequence of general relativity, that they must form whenever enough mass collapses in a small enough region. He shared the prize with the astronomers who confirmed the black hole at the center of our own galaxy. But Penrose had spent decades working on something much larger, a framework that went further than any revision to the age of the universe, eliminating the concept of a beginning entirely. He called it conformal cyclic cosmology. The core idea rests on a geometric insight. In the mathematics of general relativity, there exists a transformation called a conformal rescaling, in which you change the overall scale of space-time without altering its local geometry. Angles and shapes are preserved. Distances and durations change. Penrose noticed that the early universe, an extraordinarily hot, dense point of near-zero volume, and the far future universe, an extraordinarily cold, diffuse expanse of near-infinite volume, share a deep mathematical similarity. Under the right conformal transformation, the distant future of one universe can be mapped smoothly onto the beginning of another. In Penrose's framework, our Big Bang was a transition point, the remote future of a previous universe, transformed by conformal geometry into the fiery beginning of ours. There was no first moment. There was no creation from nothing. There was only an endless cycle of aeons, each beginning from the ashes of the last. This framework addresses one of the deepest puzzles in cosmology, the extraordinarily low entropy of the early universe. Entropy is a measure of disorder. Physicists, since Ludwig Boltzmann, have recognized that the second law of thermodynamics demands entropy to increase over time. A system that starts in a highly ordered state will inexorably move toward disorder. Our early universe was extraordinarily ordered, an incredibly unlikely starting configuration. Penrose calculated the probability of this initial state at roughly 1 in 10 to the power of 10 to the power of 123, a number so small it defies any intuitive comprehension. Why would the universe start in such an improbable state? Conformal cyclic cosmology offers an answer. At the end of each aeon, the universe has expanded until it contains only massless particles, such as photons and gravitational waves. Massless particles do not experience time in the conventional sense and carry no intrinsic sense of scale. The vast, cold, empty, late universe, measured in terms of its available degrees of freedom, has very low entropy. That state, conformally mapped, becomes the hot, dense, ordered beginning of the next aeon. Low entropy is inherited from the previous cycle. The universe does not begin in an improbable state by accident. It inherits that state as a natural consequence of what came before. This is not mysticism. It is differential geometry applied to general relativity. Penrose went further. He predicted that this cycle would leave observable traces, specific patterns in the ancient light of the cosmic microwave background, faint circles where the energies of the previous aeon had bled through into ours. Those patterns, he claimed, were already there, waiting to be found. In 2010, Roger Penrose and his collaborator Vahe Gurdzadyan published a paper making one of the most extraordinary claims in modern cosmology. They had found evidence of the universe that existed before our Big Bang. The evidence came from the cosmic microwave background, the ancient glow that Planck and its predecessor satellites had mapped with such precision. Penrose and Gurdzadyan said they had identified circular regions in the data where the temperature fluctuations were unusually smooth, rings of calm in an otherwise rippling sky. They called these features Hawking points, named in honor of the late physicist Stephen Hawking, and proposed that each ring marked a location where a supermassive black hole merger in the previous aeon had released an enormous burst of gravitational energy that propagated into our own aeon, leaving its imprint in our early universe's plasma. Black holes in the previous universe, growing for billions of years, eventually merging in catastrophic collisions. The gravitational shock waves from those collisions translated through the conformal bridge between eons, emerging as faint circular anomalies in the light we call the cosmic microwave background. If this interpretation is correct, then the ancient glow above us is not merely a snapshot of our universe's infancy. It is a palimpsest, a document written over, carrying faint traces of the cosmos that came before. Our Big Bang was a transition. There was history before our history. The response from the scientific community was immediate and deeply skeptical. Multiple independent groups analyzed the same Planck data. Their conclusion, published in subsequent papers, was that the circular features Penrose and Gurdzadyan identified are statistically consistent with ordinary random fluctuations in the cosmic microwave background. In a sky filled with temperature variations following known statistical distributions, you expect to find concentric ring-like patterns by chance. The patterns Penrose identified, the skeptics argued, are not anomalously smooth. They are exactly what you would predict from any random realization of a standard cosmic microwave background. This is a genuine scientific dispute. The claim is that subtle patterns in ancient light betray the existence of a previous universe. The counterclaim is that those patterns are ordinary noise. Both sides agree on the data. The disagreement is about what the statistics mean. Penrose has not retreated. A paper in 2013 offered refined analysis and maintained the detection. As of 2026, this question is unresolved and open. What makes it significant in this larger story is what it implies if Penrose is right. It would mean that the concept of the universe having an age is, in a deep sense, the wrong question. Our universe is 13.8 billion years old, measured from our Big Bang. But the aeon before ours stretched for an incomprehensible duration before that. The universe, in its totality, has no age at all. It has always existed. That prospect, cosmic history without a beginning, is philosophically staggering. Whether it is also scientifically correct depends on a debate still playing out in journals and conference halls around the world. And while Penrose was arguing about rings in ancient light, another physicist was pointing at something different, a theory that had quietly predicted the James Webb Space Telescope's discoveries 25 years before the telescope ever launched. In 1983, an Israeli physicist named Mordechai Milgram published 3 papers in the Astrophysical Journal that proposed a simple modification to Newton's laws of motion. At everyday accelerations, Newton's second law works exactly as described. Force equals mass times acceleration. The physics is clean and well tested, but Milgram noticed that galaxies rotate in a way that contradicts Newtonian gravity unless you add large amounts of invisible mass. The farther you go from a galaxy's center, the slower the rotation should become, just as the outer planets of our star system orbit more slowly than the inner ones. Instead, galaxy rotation curves flatten out. Stars at the outer edges of galaxies move just as fast as stars near the core, as though something is pulling them that we cannot see. The standard response was to invent dark matter halos, vast invisible shells of unknown particles surrounding every galaxy, providing the extra gravitational pull needed to explain the observations. Milgram proposed something different. What if, at very low accelerations, the relationship between force and motion changes? The force itself would remain the same, but the way matter responds to it would shift fundamentally. Below a critical threshold of acceleration, roughly 1/10,000,000th of a meter per second squared, an almost incomprehensibly small value, gravity becomes stronger relative to mass than Newton's equations predict. Galaxy rotation curves flatten naturally, with no dark matter required. Modified Newtonian dynamics, which researchers in the field refer to by the shorthand, formed from its initial letters, was met with skepticism from the mainstream. It was mathematically inelegant. It lacked a fundamental theoretical basis. It seemed like a fit to a specific observation rather than a principle of nature, but it kept making predictions that came true. The relationship between a galaxy's total mass in ordinary matter and its rotation speed, a quantity called the baryonic Tully-Fisher relation, follows an exact power law in modified Newtonian dynamics. This was a prediction, not a fit. Observations confirmed it across galaxies spanning a range of 4 orders of magnitude in mass. Clusters of galaxies, dense groups of thousands of galaxies bound by gravity, showed more tension with the theory, but isolated galaxies continued to validate it with each new generation of data. Then came the prediction that matters most for this story. In 1998, a researcher named Robert Sanders used modified Newtonian dynamics to model how structure forms in the early universe. His conclusion: galaxies form earlier and more efficiently in a universe governed by modified gravity than in one governed by dark matter halos. Specifically, Sanders predicted that objects of galaxy mass would be among the first virialized structures to form in the universe, reaching completion by redshift 10. In the same year, the Standard Model, with its dark matter halos, predicted that present-day galaxies like our own assembled their mass recently, at redshifts below 1. One theory said massive galaxies at redshift 10. The other theory said massive galaxies would not arrive until much later. In 2022, the James Webb Space Telescope launched. By 2023, it had found massive galaxies at redshift 10, 11, 12, and beyond. One theory got its prediction right 25 years in advance. The other got it wrong. The implications of that scorecard, for dark matter, for the Standard Model, and for the age of the universe, are what the next part of this story is about. For 50 years, scientists have known that galaxies spin too fast. The math does not work. The physics does not work. At the edges of a spiral galaxy, stars orbit the center at velocities that should fling them outward into the void, if the only gravitational anchor were the stars and gas we can see. So, physicists invented something new, They called it dark matter. The idea was elegant in its desperation. Galaxies must contain vast halos of invisible mass, spread far beyond the visible disk, providing the extra gravitational pull needed to keep those fast-moving stars in orbit. Nobody had ever seen this dark matter. Nobody could catch it in a detector. Nobody could create it in a laboratory. But the rotation curves demanded it, and so the universe was declared to be 27% composed of something that has never once been directly observed in the history of science. Here is where Rajendra Gupta's model introduces a different kind of uncomfortable thought. In Gupta's framework, the fundamental coupling constants of nature do not stay fixed. They weaken as the universe expands. And if the constants that govern how forces work are changing over time, then the gravitational force law itself behaves differently across cosmic history. Galaxy rotation curves that seem to require invisible mass in one mathematical framework explain themselves naturally in another. The dark matter disappears from the equations, not because it was removed arbitrarily, but because the physics that demanded it was itself incomplete. This is not the first time a model has done this. Modified Newtonian dynamics, the gravity theory proposed by Israeli physicist Mordechai Milgrom in 1983, has been predicting galaxy rotation curves without dark matter for 4 decades. Galaxy after galaxy, Milgrom's framework matches the observed velocities using only visible matter and a modification to how gravity behaves at very low accelerations. No invisible particles required, no halos made of unknown substances, just a different relationship between force and acceleration at the outermost, slowest moving edges of a galaxy. The standard model has never explained why the critical acceleration at which Milgrom's modification kicks in happens to equal approximately the speed of light, multiplied by the current cosmic expansion rate. That numerical coincidence links the behavior of individual galaxies to the expansion of the entire universe. In 50 years of dark matter searches, no one has been able to explain that link. In modified Newtonian dynamics, it is built into the foundation. Now add the Gupta layer. If coupling constants vary over cosmic time, the force law shifts. If the force law shifts, galaxy dynamics change. The same rotation curves that seemed to demand invisible mass now emerge from visible matter operating under different rules. Both approaches reach the same conclusion from different directions. The dark matter problem may be a measurement problem dressed up as a substance problem. The scientific community has spent roughly 50 years building detectors, running experiments, and designing underground laboratories to catch a dark matter particle. None have succeeded. The Large Hadron Collider produced no dark matter candidates. Underground liquid xenon detectors found nothing. Satellite experiments searching for dark matter signals in the galactic center returned only silence. Occam's razor asks a pointed question. What if the simplest explanation is that dark matter was never there to begin with? What if the universe is older, the forces are different, and the invisible scaffold we built was holding up a misunderstanding? The skeptics have been listening to all of this. Their arguments are harder to dismiss than you might think, and they deserve a full hearing before the verdict comes in. Before the revolution gets too comfortable, it is worth listening to the people who think it is not a revolution at all. The mainstream cosmological community is not panicking. They are watching the James Webb Space Telescope data come in, acknowledging the genuine surprises, and offering a quieter explanation for all of it. Their argument, the standard model is not broken. It is being pushed to its edges by a telescope more powerful than anyone anticipated, and pushing a theory to its edges is a normal part of science. Start with the most straightforward objection. Some of the impossible galaxies may simply be misidentified. A galaxy at redshift 14 could, under certain observational conditions, mimic the color signature of a galaxy at redshift 4 that is heavily coated in dust. Dust reddening can fake cosmic distance. Photometric identification, which means selecting a galaxy's distance by its color rather than by measuring its light spectrum directly, carries real uncertainty. Before James Webb launched, most high redshift galaxy candidates were selected this way. Some candidates have already been corrected downward when spectroscopic confirmation was obtained. The scientific community is careful here. This matters. But spectroscopic confirmation has been obtained for the most dramatic cases. The galaxy designated JADES GSZ 140 was measured with actual spectrum analysis. The oxygen emission line was detected. The redshift is real. The establishment knows this. So their second argument shifts to astrophysics rather than measurement error. Perhaps star formation in the early universe was simply more efficient. In the local universe, only a few % of available gas actually turns into stars. The rest is blown away by stellar winds, supernova shock waves, and radiation pressure. But in the denser, more compressed early universe, those feedback mechanisms may have been weaker. Perhaps the initial mass function, the statistical distribution of how massive newborn stars tend to be, was skewed toward the heavy end. Heavier stars burn faster, explode sooner, and enrich their galaxies with heavy elements in a fraction of the time lighter stars require. Under these assumptions, the standard model can accommodate most of what James Webb has found. Most, not all. The cosmic microwave background remains the establishment's strongest card. No alternative model has matched the precision of the standard model's fit to the background radiation. 35 acoustic peaks across a vast range of angular scales, reproduced to astonishing accuracy by a model whose parameters were tuned before the measurements were made. That is not a coincidence. That is a theory working correctly, and there is the time dilation evidence. When a distant supernova explodes, the shape of its brightening and fading stretches in time in proportion to its redshift. A supernova at redshift 1 takes twice as long to fade as a local one. This is exactly what an expanding universe predicts. Tired light, the theory that redshift comes from photons losing energy rather than space stretching, predicts no time dilation at all. The Dark Energy Survey's supernova program confirmed this stretching to high statistical confidence. That result is a direct measurement of cosmic expansion, and it is hard to explain away. The establishment is not wrong to make these arguments. The standard model has survived 50 years of precision tests. The question now is whether it can survive what James Webb keeps sending back. And one star in our own galaxy has been making cosmologists nervous for far longer than any space telescope has existed. It sits in our own galaxy. No exotic telescope required. No redshift measurements. No spectroscopic confirmation of ancient light from the dawn of time. Just a star, close enough to see with binoculars on a clear night, that by some estimates should not exist. Astronomers call it the Methuselah star. Its catalogue designation is HD 14283, and for decades it has been one of the most uncomfortable objects in observational astronomy. Not because it is strange to look at, because of what measuring its age implies. Stars have a clock built into their chemistry. As a star ages, it burns through its hydrogen fuel, and its position on a diagram plotting temperature against luminosity shifts in predictable ways. By looking at where a star sits on that diagram and comparing it to models of stellar evolution, astronomers can estimate how long it has been burning. The older the star, the lower its content of heavy elements, because it formed before the universe had produced much of anything beyond hydrogen and helium. The Methuselah star is extraordinarily metal poor. It belongs to a population of ancient stars that formed in the earliest era of our galaxy. When astronomers first applied modern dating techniques using satellite data in the early 2000s, the age they obtained was startling, 16 billion years. Older than the universe itself, that number was immediately challenged. Systematic uncertainties in stellar models, distance measurements, and chemical composition all introduce error. A 2013 study using the Hubble Space Telescope brought the estimate down to 14.46 billion years, with an uncertainty of 800 million years in either direction. That uncertainty range barely overlaps with 13.8 billion. A 2024 study using the planet-finding Transiting Exoplanet Survey satellite found 14.2 billion years. A different 2024 analysis using refined chemical abundances arrived at 12.3 billion years. The range runs from 12.3 to 14.46. The universe is 13.8 billion years old. The overlap is thin enough to make cosmologists sweat. Here is why this matters beyond a single star. The Methuselah star is not alone. Globular clusters, the ancient gravitational families of hundreds of thousands of stars orbiting the outer regions of the Milky Way, contain stars whose ages cluster between 12 and 13.6 billion years. The oldest of these push close against the universe's claimed age. Stellar chronometers are independent measurements. They do not rely on the cosmic microwave background, on supernova distances, on expansion rate estimates. They read age directly from nuclear physics. If the universe is 13.8 billion years old, there is almost zero margin. The Methuselah star must be at the low end of every uncertainty range simultaneously. Every assumption in every stellar model must lean in the right direction that is possible. It is also deeply uncomfortable. In Gupta's 26.7 billion year universe, the Methuselah star is simply old. 12 to 14 billion years is nowhere near the limit. It formed early, burned slowly, and it is still there. No paradox. No nail-biting overlap of error bars. Just an ancient star doing what ancient stars do. The star does not prove the universe is older, but it refuses to let the question close. And the next measurement making cosmologists nervous is not about a single old star. It is about the very yardstick we use to measure everything. Two teams of scientists are measuring the same thing. They are using different methods. They are getting different answers. And the gap between those answers is not getting smaller as the data improves. It is getting larger. This is the Hubble tension, and it is one of the most serious unresolved problems in all of modern physics. The Hubble constant describes how fast the universe is expanding. Measure it from the cosmic microwave background using the Planck satellite data and the standard model, and you get 67.4 kilometers per second for every unit of cosmic distance spanning roughly 3.2 million light years. Measure it locally using the distances to exploding stars and pulsing variable stars in nearby galaxies, and you get 73 kilometers per second for that same unit of distance. These numbers disagree at a level of statistical confidence exceeding 5 sigma, which, in physics, is the threshold above which coincidence becomes crisis. A higher expansion rate means the universe reached its current size more quickly. Work it backward. If the universe is expanding faster than the background radiation suggests, it is younger. The local measurement implies a universe approximately 12.9 billion years old. The background radiation implies 13.8 billion. The same universe, measured with two different rulers, gives two different ages separated by nearly a billion years. Something is wrong. The question is what? One possibility: our local yardsticks are broken. The chain of distance measurements used to determine the local expansion rate depends on Cepheid variable stars, which pulsate at rates tied to their true luminosity. If those calibrations are slightly off, the local measurement shifts. James Webb has been re-examining the Cepheid distance ladder, and while some corrections were made, the core tension has not resolved. Another possibility: something happened in the early universe that altered the expansion rate before the cosmic microwave background was imprinted. A brief pulse of anti-gravitational force, acting for the first 100,000 years, could shift the acoustic peaks in a way that biases the background toward a misleading implied age. This is the early dark energy hypothesis, which gets its own chapter ahead. A third possibility, more radical: the standard model is wrong about dark energy. If the mysterious force accelerating cosmic expansion is dynamic rather than constant, the entire age calculation changes with it. In early 2026, A study published in a major European astronomy journal used stellar age data from the European Space Agency's Gaia mission to independently constrain the universe's age from the oldest Milky Way stars. The result supported the older age, implied by the background radiation, and strongly disfavored the younger universe implied by local distance measurements. Critically, the Gaia result placed a lower bound on the universe's age. Stars can be old if the universe is older than we thought. They cannot be older than the universe. This is the asymmetry the skeptics rarely mention. Every stellar clock that ticks too long for the standard model supports the possibility of an older cosmos. No stellar clock has ever confirmed that the universe is younger than the stars within it. The Hubble tension is not just a measurement dispute. It is a signal that something fundamental about our understanding of cosmic expansion is incomplete. And the next crack in that understanding came from an entirely unexpected direction. The Nobel Prize sits at the center of this chapter, and by the end, its foundation will look considerably less solid. In 1998, two independent research teams made the most startling discovery in cosmology since the cosmic microwave background was found. They were measuring the distances to exploding stars, specifically a class of stellar explosions called Type Ia supernovae, using them as cosmic measuring sticks. These explosions are extraordinarily useful because they all reach approximately the same peak brightness, making them reliable reference points for calculating cosmic distances. What the teams found was that the most distant supernovae were fainter than expected. If the universe were expanding at a constant rate, or even slowing down under gravity's pull, those ancient explosions should appear at predictable distances. Instead, they were farther away, which meant the universe was speeding up. Something was pushing galaxies apart with increasing force over cosmic time. They called it dark energy, awarded it the 2011 Nobel Prize in Physics, and built it into the foundation of the Standard Model. In November 2025, a team at Yonsei University in South Korea published findings that quietly threatened that entire edifice. Their discovery concerned something called an age bias in supernova luminosity. It had been known for some time that Type Ia supernovae do not all explode with identical brightness. Their luminosity varies with the age of the stellar population that produces them. Supernovae from older stellar populations tend to be brighter after standard corrections. Supernovae from younger populations tend to be fainter. The standard analysis corrects for some of this variation, but the Yonsei team found the correction was incomplete. When they applied a more rigorous correction for this age-dependent luminosity bias, using 300 supernova host galaxies from the Dark Energy Survey, the data changed. The evidence for constant dark energy disappeared. In its place, the corrected data suggested dark energy that weakens over time, a repulsive force that dominated early in cosmic history, but has been fading, perhaps approaching zero, or perhaps already reversing. More dramatically, when the bias was fully corrected, the data suggested the universe may have already transitioned out of accelerating expansion. The current expansion may be decelerating. This is confirmed science from a peer-reviewed study using data from one of the most respected large-scale astronomical surveys ever conducted, applying a correction the broader community acknowledges is physically reasonable. If dark energy is not constant, then every age estimate derived from assuming it is constant is potentially wrong. The entire timeline of the universe was calculated assuming that the repulsive force filling the vacuum of space stays fixed across all of cosmic history. If that force was stronger in the past and is weaker now, the universe spent more time in a slower expanding, matter-dominated phase than the standard model accounts for. The age estimate shifts. The Nobel Prize does not disappear. The accelerating expansion was real when it was detected, but the story behind it may be more complicated than any model built in 1998 could have imagined. And the next instrument to weigh in on this question had been watching the sky for an entire year before announcing what it found. There is an instrument sitting atop a mountain in the Arizona desert that is changing the conversation faster than any single paper. The Dark Energy Spectroscopic Instrument is mounted on the 4-meter Male Telescope at Kitt Peak National Observatory. It carries 5,000 robotic fiber optic positioners, each capable of targeting an individual galaxy with precision, each feeding light into spectrographs that break it into a chemical fingerprint. In a single night, it can measure the spectra of over 100,000 galaxies. It is the most powerful galaxy survey machine ever built. In 2024, it released its first year of results. The finding that attracted most attention was not a single dramatic discovery. It was a statistical hint, a signal at the level of 2.6 sigma, meaning roughly a 1 in 100 chance it is a statistical accident, suggesting that dark energy is not constant. The measurement came from baryon acoustic oscillations. This concept deserves a pause. In the first 400,000 years after the Big Bang, the universe was a hot plasma in which sound waves were traveling. Pressure waves moved through the plasma like ripples through water, driven by the competing forces of radiation pressure and gravity. When the universe cooled enough for atoms to form, those waves froze in place. They left an imprint in the distribution of matter across the cosmos, a preferred spacing between galaxies, a characteristic scale written into the fabric of the universe itself like a ruler that will never change. By measuring that ruler at different cosmic epochs, using galaxies at different distances and therefore different points in cosmic history, astronomers can trace how the expansion rate changed over time. The Dark Energy Spectroscopic Instrument measured this ruler across more galaxies and more cosmic epochs than any previous survey. The hint of evolving dark energy appeared in the way that ruler seems to change across cosmic time in a pattern inconsistent with a perfectly constant energy. The equation of state parameter that describes how dark energy behaves appears to depart from -1, which is the value corresponding to a stable, unchanging vacuum energy. The departure is small. It is not yet definitive, but it is there, and it is consistent with what the Yonsei supernova team found through an entirely different method. 2 independent measurements, using 2 independent techniques, pointing in the same direction. Dark energy is not what we thought it was. The implications cascade. If dark energy evolves, the simple formula physicists have used to run the universe's history forward and backward in time requires modification. The moment of the Big Bang, calculated by projecting the current expansion rate backward under the assumption of constant dark energy, shifts. The age of the universe shifts with it. A universe where dark energy peaked and then declined would have spent more of its history in a slower phase of expansion than the standard model predicts. More time for galaxies to form, more time for stars to ignite and age, more time for the elements that trace those stellar generations to accumulate. The standard model is named in part after a quantity that may not be constant at all. Lambda, the symbol for the cosmological constant, may need a new name. And the question of what fills the vacuum has a potential answer that almost nobody in the mainstream was willing to hear. But one group of researchers thought they could fix the problem without replacing the model, and their attempted solution carries a surprise of its own. Not every cosmologist reaching for a solution is willing to throw away the standard model. Some are trying to save it. The proposal that gained the most traction in the academic community over 2024 and 2025 is called early dark energy. The idea emerged from collaborative research across institutions, including the Massachusetts Institute of Technology and Cambridge University, and its logic is careful and conservative. Instead of rewriting cosmic history from scratch, early dark energy adds a single ingredient to the existing recipe. The concept works like this. In the current standard model, the very early universe was dominated by radiation and matter, and gravity was gradually pulling structures together. Early dark energy proposes that for a brief window, roughly the first 100,000 years of cosmic time, a burst of anti-gravitational force acted on the universe. This extra repulsive energy then decayed away and vanished, leaving no direct trace in the present universe. The effects, however, would have been significant. During those 100,000 years, the brief acceleration would have changed the density of the cosmic plasma in ways that left subtle fingerprints in the cosmic microwave background. The acoustic peaks, those frozen sound waves that carry the Standard Model's most precise measurements, would have been slightly shifted. More crucially, the density fluctuations in the early universe would have been amplified. Larger density fluctuations mean larger gravitational seeds. Larger seeds mean larger dark matter halos form sooner. Larger halos mean more massive galaxies in the first billion years. This is exactly what James Webb found. Galaxies too massive, too early for the Standard Model to accommodate. Early dark energy provides a mechanism to make them possible without abandoning the fundamental framework. The appeal is obvious. The mainstream gets to keep its Big Bang, its cosmic microwave background fit, its dark matter halos, its general structure. It just adds one brief, early event that turbocharges the start of galaxy formation. But there is a catch, and it is a significant one. Early dark energy was originally proposed partly to solve the Hubble tension, the disagreement between the background radiation's implied expansion rate and the local measurement. The way it resolves that tension is by effectively pushing the expansion rate toward the higher local value. A faster expanding universe is a younger universe. If early dark energy forces the Hubble constant towards 73 kilometers per second per unit of cosmic distance, the universe becomes younger, settling at approximately 13.2 billion years rather than 13.8. That is the wrong direction for the Methuselah star. A universe 600 million years younger than the Standard Model has even less room for stars that date back close to the beginning. The stellar age problem, already uncomfortable, gets worse, and early dark energy cannot explain everything James Webb has revealed. It can build bigger galaxies earlier. It cannot explain what those galaxies look like up close. It cannot explain the spiral arms on galaxies that should be far too young to have them. It cannot explain the retired star-forming systems that had already finished their entire life cycle before the universe supposedly reached its first birthday. It patches one leak while leaving others open. The uncomfortable truth about early dark energy is that it is a clever fix for a subset of the problem. The deeper question is whether the problem itself is demanding something more fundamental. James Webb has one more category of discovery that no patch addresses, and it involves something cosmologists thought they understood completely: the shape of a galaxy. If you could look at the Milky Way from above, you would see a shape that took billions of years to build. Spiral arms sweep outward from a central bulge, carved by density waves traveling through the galactic disk like grooves on a spinning record. Stars in those arms tend to be younger, still forming from compressed gas. The inner regions are older, filled with cooler stars that ignited when the galaxy was young. The disk itself is thin because the gas settled over billions of years of collisions and gravitational interactions into an ordered, rotating plane. Astronomers who study galaxies have spent decades calculating how long that kind of structure takes to develop. The answer involves multiple mergers, repeated cycles of gas infall and star formation, and the gradual dissipation of chaotic orbits into the smooth, ordered rotation of a mature spiral disk. Conservative estimates put the timescale at several billion years. More careful models push it longer. James Webb has found spiral galaxies at redshift 6. In the Standard Model, that redshift corresponds to a universe less than 1 billion years old. This is confirmed. These are not photometric candidates selected by color and awaiting spectroscopic verification. Multiple teams have examined these objects in detail. They have clear arms, they have central bulges, they show ordered rotation in their gas and stellar distributions. One galaxy in particular, studied by teams examining James Webb data in 2024, showed two distinct spiral arms, with a morphology indistinguishable from local spiral galaxies that have been evolving for most of cosmic history. The simulations cannot reproduce this. The most sophisticated computational models of galaxy formation tracking hundreds of millions of particles representing dark matter, gas, and stars, running on some of the most powerful supercomputers in the world, produce early galaxies that are chaotic, irregular, and clumpy. They have never produced spiral structure at redshift 6, when researchers have attempted to force their simulations to match the James Webb observations. The models require conditions that stretch their physical assumptions past the point of comfort. Two explanations survive this confrontation. The first, galaxy formation physics is fundamentally incomplete. Our models are missing something about how gas cools, how feedback operates, how dark matter halos shape the baryonic structures inside them. The spiral arms are a symptom of ignorance in our models. The second, the timeline is wrong. If the universe at redshift 6 is several billion years old, rather than less than 1 billion, the spiral structures have time to develop through the same processes that built the Milky Way. The galaxies are not extraordinary. The clock we assign to them is. Both explanations allow the universe to make sense. Only one of them requires rewriting cosmic history. The other requires admitting that our models of galaxy formation are missing something large, something fundamental, something that decades of simulation and observation have failed to identify. The impossible spiral galaxies are not alone in their challenge. Alongside them, James Webb found something even harder to explain: galaxies that had already lived their entire lives. A galaxy is alive when it is making stars. Gas collapses under gravity, heats up, ignites, and a new star is born. That star lives for millions or billions of years depending on its mass, then dies, releasing heavy elements back into the gas that will seed the next generation. The cycle repeats, building a richer and more complex galaxy over time. A galaxy is dead, or quenched in the language astronomers use, when it has stopped making stars entirely. The gas is gone. The star formation has shut down. What remains is a population of aging, reddening stars slowly cooling toward darkness. These retired galaxies are common in the local universe. They are typically large, massive, and old. They exist because galaxies eventually consume their fuel. James Webb found quenched galaxies at redshift 5 and redshift 6, galaxies that had already stopped forming stars when the universe was supposedly less than 1 billion years old. Think carefully about what that requires. A galaxy at redshift 5 that has already quenched must have formed its stars, built up its stellar mass, exhausted its gas supply, and shut down all star formation, all within the first billion years of cosmic time. In the standard model, that is nearly instantaneous on cosmological scales. 1 billion years is roughly 7% of the current age of the universe. Running a complete galactic life cycle, from formation through enrichment through retirement, in 7% of all available time requires efficiencies that strain the physics of star formation past credibility. And these are not small galaxies. Some of the quenched systems James Webb found at these extreme redshifts carry stellar masses comparable to large galaxies in the present-day universe. They formed quickly, they built up enormous mass, and then they stopped, before the universe had finished what we called its infancy. The principle here is simple and difficult to escape. Retirement requires a working life. A galaxy cannot quench before it has time to form. If the universe was genuinely less than 1 billion years old when these galaxies were already dead and cold, then something is wrong with the standard timeline, with our models of star formation, or with both. This is where Gupta's model offers one of its most concrete explanations. In the standard framework, a galaxy at redshift 6 existed when the universe was approximately 900 million years old. In Gupta's 26.7 billion year universe, the same galaxy existed when the universe was approximately 4.5 billion years old. 4.5 billion years is enough time for a galaxy to form, accumulate stellar mass, enrich its interstellar medium with heavy elements, and exhaust its star-forming gas. It is enough time for a complete galactic life cycle, start to finish. The quenched galaxies are not paradoxes in a 26 billion year universe. They are the expected outcome of galaxies that formed early and aged normally. Their retirement makes sense if the universe gave them enough time to work. Whether that explanation is correct depends on evidence still being gathered. But the next piece of that evidence involves a specific element detected in the most distant spectroscopically confirmed galaxy ever found, and it makes the case harder to dismiss than any spiral arm or retired stellar population. The chemistry of the early universe is about to become the most uncomfortable evidence of all. Oxygen is not free. Every atom of oxygen in the known universe was forged inside a massive star in the final chapters of that star's life. In the cores of stars at least 8 times more massive than an ordinary star, nuclear fusion builds carbon, neon, and eventually oxygen through a series of reactions that take millions of years to complete. When the star exhausts its fuel, it collapses and explodes in a supernova, scattering the oxygen it produced across the surrounding space. That oxygen then drifts through the interstellar medium, cools, and eventually becomes part of the next generation of stars, planets, and in at least one corner of the universe, breathing creatures. This process has a minimum duration. From the ignition of the first massive star to the oxygen scattered by its death, you need at minimum tens of millions of years. More realistically, because the first generation of stars must form, produce the heavy elements that help the next generation cool and collapse, and then die, you need at least 100 million years before a meaningful amount of oxygen is available to be detected in a galaxy's spectrum. In 2024, the James Webb Space Telescope detected ionized oxygen in the galaxy designated JADESGSC 140. That galaxy was observed at a redshift of 14.32. In the standard model, that redshift corresponds to a cosmic age of 290 million years after the Big Bang. 290 million years. That is the total time from the beginning of everything to the moment James Webb captured that galaxy's light. And in that time, according to what the spectrum shows, entire stellar populations had already been born, had forged oxygen in their cores, and had already died in explosions that scattered that oxygen into the galaxy's surrounding gas. The Discovery team stated it directly. The presence of oxygen implies that star formation must have begun well before the 290 million year mark, at minimum 100 million years earlier, at the very beginning of the Standard Model's timeline for the universe emerging from the cosmic dark ages. There was simply no room. This is confirmed. This is not a photometric estimate. This is a spectral line, identified with the precision of laboratory measurements, in the most distant galaxy whose distance has been directly verified. The oxygen is real. The timeline implied by the oxygen is real. The conflict with the Standard Model is real. In a 26 billion year universe following Gupta's model, the same galaxy existed when the universe was approximately 3.5 billion years old. 3.5 billion years is longer than the time it took for complex life to emerge on Earth after the planet formed. It is more than enough time for multiple generations of massive stars to form, burn oxygen into existence, and die. The oxygen in JADESGSC 140 is unremarkable in that timeline. It is the natural product of stars doing what stars do, over billions of years, in a universe old enough to let them finish the job. In the Standard Model, those same stellar generations had to accomplish everything in a window barely wider than the blink of a cosmic eye. The oxygen problem is chemical. It is direct. It involves the most fundamental process in stellar physics. And it sits at the heart of why the impossible early galaxy problem is not a curiosity waiting to be explained away by a better simulation. It is a signal that the universe has been keeping time differently than we assumed. The next question is what that signal means for everything we thought we built on solid ground. Some of the most alarming galaxies JWST has discovered have never had their distance confirmed the hard way. That is not a minor detail. It is the center of one of the most important debates in modern cosmology, and understanding it changes how you interpret everything that came before in this story. Here is how astronomers find galaxies at extreme distances. Light from a distant galaxy arrives stretched by the expansion of space. The further the source, the more stretched the light. A galaxy at redshift 10 is seen when the universe was roughly 450 million years old by the Standard Model. At redshift 14, the light has been traveling for more than 13.5 billion years. Each redshift value translates directly into a cosmic epoch, a moment in the history of everything. The cleanest way to measure redshift is spectroscopy. Split the incoming light into its component wavelengths, identify known spectral lines, and measure how far they have shifted toward the red end of the spectrum. This is the gold standard. It requires bright sources, long observation times, and a working spectrograph. It is slow and expensive in telescope hours. The faster method is photometry. Measure how bright a galaxy appears through a set of color filters. If it drops off sharply in the blue and appears only in the redder bands, that suggests high redshift. The color pattern mimics a spectral signature. It is efficient. It allows surveys to identify hundreds of candidate distant galaxies in a single observation field. But color can lie. A galaxy heavily cloaked in dust scatters and absorbs short wavelength light. From a distance, a dusty galaxy at redshift 4 can produce a color signature that looks remarkably like a clean galaxy at redshift 12. Without a spectrum, you cannot always tell them apart. Some objects that once appeared in headlines as record-setting distant galaxies were later observed spectroscopically and turned out to be closer, dustier systems masquerading as cosmic pioneers. This is the photometric trap, and it is legitimate. Scientists know it exists. They worry about it. Some fraction of the impossible galaxy candidates may belong to it. Then comes the moment that shifts the ground beneath that argument. J, A, D, E, S, G, S, Z, 140 was spectroscopically confirmed. The team did not guess its distance from colors. They pointed the near-infrared spectrograph instrument directly at it, split its light into component wavelengths, and measured the oxygen emission line directly. That line placed the galaxy at redshift 14.32. The measurement does not move. The oxygen is real. The redshift is real. The galaxy is exactly where the data say it is. And beyond that single object, the confirmation rate for high redshift candidates has climbed steadily. Multiple galaxies above redshift 10 have now been spectroscopically verified. Each new confirmation closes one escape hatch for the Standard Model. Each one asks the same quiet, relentless question. If even a handful of these are genuinely there, how did they get there so fast? The photometric trap is a real concern. Science should apply it rigorously, but the trap does not swallow everything. The confirmed cases alone are enough to sustain the crisis. They are enough to demand an explanation that goes beyond cautionary methodology. And now that the skeptics have had their first say, the crisis is about to meet its most formidable challenge yet, because the simulations that were built to explain the universe are starting to break down. For decades, cosmologists have not just observed the universe, they have built it. Starting in the 1980s and accelerating through the 21st century, computational physicists assembled virtual universes inside supercomputers. They seeded these simulations with the density fluctuations measured in the cosmic microwave background, then let time run forward. Gravity pulled matter together. Dark matter collapsed into halos. Gas fell in, cooled, and ignited into stars. Galaxies formed, merged, and grew. By the time JWST launched, these simulations had become extraordinarily sophisticated. The most relevant were known as the Renaissance simulations. Built to model the first billion years of cosmic history, they required millions of computing hours on some of the world's most powerful machines. They encoded the best available understanding of hydrogen chemistry, ultraviolet radiation feedback, supernova explosions, and dark matter dynamics. They were, in effect, a controlled test. Run the Standard Model, see what universe it produces. For years, they mostly matched observations. Then JWST started sending data home. A study published in 2025 compared JWST's confirmed high redshift galaxies directly against what the Renaissance simulations predicted should exist at those epochs. The results were sobering. Most galaxies, at redshift 10 to 12, could be accommodated, pushed to the edges of what the simulations allowed, but held within their limits. The theorists breathed. Then came the outliers, JADES GSZ140, and its companions at redshift 14 and above pushed past the simulation's outer boundaries. These galaxies were more massive, more luminous, and more chemically evolved than the most optimistic outputs the models could generate. The simulations had been tuned on decades of observation. They were built to handle surprises. They were breaking anyway. The cosmological community's response was to propose modifications. Perhaps the initial mass function, the distribution of stellar masses at birth, was skewed in the early universe toward massive stars that burned fast and furious. Perhaps the first star-forming clouds were uniquely efficient, collapsing without the feedback that normally slows star formation in later epochs. Perhaps primordial black holes seeded galaxy formation before ordinary gravity had time to act. Perhaps accretion onto those black holes exceeded the theoretical rate known as the Eddington limit. These are legitimate scientific proposals. Researchers have published serious papers on each of them, but they share a structural problem. They are patches. Each one adds a layer of unconfirmed physics to a framework that was supposed to work without those additions. Each one requires behavior that has never been directly observed in the universe to explain behavior that has been. There is a name for this in philosophy of science: ad hoc modification. It is what happens when a theory is confronted with data that does not fit, and rather than questioning the theory, practitioners invent new mechanisms to absorb the contradiction. The theory survives, but it grows more complicated with each rescue. The simpler possibility that the theory is wrong about the timeline becomes harder to dismiss. The simulations were supposed to be a triumph of the standard model. They still contain real physics and real predictive power. But at the frontier JWST keeps pushing into, they are struggling to keep up. And that frontier is about to be defended by the strongest argument the establishment has: the cosmic microwave background, the bedrock evidence that has anchored our understanding of the universe for half a century. The skeptics are about to take the floor one final time. Science is at its best when it refuses to be rushed. Before anyone declares the standard cosmological model broken, there is a case to be made for its continued power. And that case deserves to be stated clearly and taken seriously on its own terms, because most cosmologists, even after 3 years of JWST data, have not abandoned the framework that has served them for 50 years. Begin with the strongest piece of evidence in all of cosmology. The cosmic microwave background is not just a warm glow of ancient light. It is a precise fingerprint of the early universe, encoded in patterns of temperature variation spanning the entire sky. The mathematical structure of those patterns, described by the angular power spectrum, contains 35 identifiable peaks across scales ranging from the size of the observable universe down to fractions of a degree. Each peak represents a specific acoustic oscillation in the plasma of the early universe, and each one is sensitive to the exact composition of matter, the geometry of space, and the expansion history of the cosmos. The standard model fits all 35 of those peaks, precisely, within measurement uncertainties, using a small number of free parameters. No alternative model has achieved this. The tired light hypothesis cannot reproduce the thermal spectrum of the microwave background. Rajendra Gupta's covariant coupling constants plus tired light model has not been shown to match all 35 acoustic peaks simultaneously. Roger Penrose's conformal cyclic cosmology makes no prediction for the detailed structure of the power spectrum. This is not a small thing. It is the most precise measurement in the history of astronomy. Then there is the confirmation of expansion itself. The Dark Energy Survey Supernova Program published a landmark result confirming that Type Ia supernova light curves at high redshift take longer to evolve, exactly as expansion predicts. A supernova at redshift 1 fades more slowly than a nearby one by precisely the factor that cosmic expansion would stretch time. Tired light models, which propose redshift without expansion, predict no such stretching. The observation rules out pure tired light at high statistical confidence. The baryon acoustic oscillation measurements, independently gathered by multiple surveys over 2 decades, provide a standard ruler embedded in the large-scale distribution of galaxies. Measurements from the dark energy spectroscopic instrument alone now span billions of galaxy spectra. They constrain the expansion history with a precision that rules out wildly different timelines. Big Bang nucleosynthesis remains a triumph. The abundances of hydrogen, helium, deuterium, and lithium forged in the first 3 minutes depend sensitively on the expansion rate and particle density at temperatures of 1 billion degrees. The standard model predicts the ratios we observe with extraordinary accuracy. Changing the early expansion history, as many alternative models require, would break these predictions. The establishment's position is clear. JWST reveals genuine tensions in the predictions of early galaxy formation. This is a real problem. It will require new physics, probably in the astrophysics of star formation rather than in the cosmological timeline. But the timeline itself, anchored by the microwave background, the supernova time dilation, and the acoustic oscillation scale, has not been defeated by a collection of massive early galaxies. The standard model has problems. It also has extraordinary successes. What comes next is not a verdict. It is the beginning of a deeper synthesis, one that may require holding both the establishment's evidence and the anomalies with equal seriousness. Because when you lay both sides of this argument on the same table, something unexpected comes into focus. Every anomaly we have encountered in this story has had its own architect. Fritz Zwicky saw photons losing energy across cosmic distances and proposed a universe older than the expansion implied. Rajendra Gupta built a framework where the forces of nature themselves weakened over time, stretching the cosmic calendar to 26.7 billion years. Roger Penrose looked at the mathematical structure of space-time and found a universe that was never born and will never die, cycling through endless eons. Mordechai Milgram changed the law of gravity at low accelerations and predicted massive early galaxies a full quarter-century before JWST confirmed they existed. These models developed independently. They emerged from different traditions, different mathematical frameworks, different intellectual temperaments. Their authors do not form a school. They have not signed a joint manifesto. And yet, when you arrange their findings side by side, a coherent challenge to the standard model takes shape. Each model attacks a different foundation. Tired light questions whether all redshift comes from expansion. Covariant coupling constants question whether the laws of physics have been the same since the beginning. Conformal cyclic cosmology questions whether there was a beginning at all. Modified Newtonian dynamics questions whether dark matter exists in any form. Together, they are not random descent. They are a systematic pressure test applied to a model that was built on assumptions that seemed reasonable in the 20th century but have never been independently confirmed at the depths JWST is now exploring. Here is the meta-argument that ties them together. The standard model was constructed to fit a specific dataset, the cosmic microwave background, as measured through the 1990s and 2000s, the supernova distance ladder as calibrated before modern instruments, the galaxy surveys available before high-precision spectroscopy was routine. It fit that dataset brilliantly, but the data available at any moment in history is always incomplete. A theory that fits incomplete data perfectly can still be wrong in ways that only become visible when new instruments push to previously inaccessible frontiers. JWST is such a frontier. It peers into an epoch that was essentially unobservable before 2022. The galaxies it finds there were always out there. We simply lacked the instruments to see them. And what it sees challenges the predictions that were made with confidence about what that epoch should look like. The standard model says the early universe should be populated by small building block proto-galaxies gradually assembling through mergers over hundreds of millions of years. JWST finds massive, mature, chemically enriched systems that appear to have been born ready. The gap between prediction and observation is not a rounding error, it is a structural failure. The alternative synthesis does not require choosing between Zwicky, Gupta, Penrose, and Milgram. It requires recognizing that the failure is real enough to take all of them seriously. Each offers a piece of an explanation. Together, they suggest that the standard model may be a comfortable wrong answer that fit the data available at a particular moment in the history of inquiry. None of these alternatives is complete. None has matched the full precision of the cosmic microwave background fit. The work is unfinished. But the conversation has changed. 4 years ago, anyone questioning the age of the universe was a crank. Today, they have a telescope on their side. And the deeper the telescope looks, the stranger the universe becomes. There is a question hiding beneath every number in this story. When we say the universe is 13.8 billion years old, what exactly are we measuring? Age is something we understand intuitively from our own lives. We measure it in years, which are defined by the orbit of a planet around a star, which is itself moving through a galaxy, which is moving through the fabric of expanding space-time. The ground beneath the number is not as solid as it feels. In everyday experience, time flows at the same rate everywhere. 1 second for you is 1 second for someone across the room. But general relativity, the framework Einstein published in 1915, tells us this is an approximation that works only because we live in nearly identical gravitational conditions. Near a massive object, time slows down. Moving at high velocity, time slows down. These effects are real, measurable, and already factored into the systems our technology relies on to function. At cosmological scales, the complications multiply. When cosmologists calculate the age of the universe, they are calculating the elapsed time since the Big Bang, as measured by an idealized observer who has been at rest relative to the cosmic expansion since the very beginning. This is called cosmic time, and it is a mathematical construct rather than something any physical observer could directly experience. It is the age of the universe from no particular place within it, but we are not at rest relative to the cosmic expansion. Our galaxy has a peculiar velocity relative to the cosmic microwave background of roughly 600 kilometers per second. Galaxies in clusters move relative to one another at thousands of kilometers per second. The universe contains no frame that is truly at rest. Every observer is embedded in a local gravitational environment that modifies the flow of time relative to the cosmic average. These corrections are small for a system like ours. They do not shift the age of the universe by billions of years, but they reveal something important about the nature of the question itself. If the fundamental constants of nature have been evolving, as Rajendra Gupta proposes, then the rate at which physical clocks tick has not been constant over cosmic history. The atomic transitions that define our units of time depend on the coupling constants of electromagnetism and nuclear forces. If those constants were different in the early universe, then a second in the first billion years was not the same duration as a second today, at least as measured by the physics we currently use to define what measurement means. Age is observer-dependent. It depends on the physics of the clock. This is more than philosophical speculation. A universe where coupling constants evolve is a universe where the question of how old something is requires specifying what kind of clock you are using to answer it. The 26.7 billion years Gupta calculates is an age measured in today's units, projected backward through a history where the units themselves were changing. That does not make the number meaningless. It makes the interpretation richer and more careful. The universe may be older in terms of physical processes, in terms of how many stellar generations could have formed and collapsed and seeded the cosmos with heavy elements, than our standard clocks suggest. We are not measuring one fixed thing. We are measuring the universe's history through the lens of our own moment in time. And the next question, the one no instrument has yet answered, is even harder to ask. The crisis JWST created will not be resolved overnight, but the instruments being built to resolve it are unlike anything science has had before. Start with what is already in motion. The Dark Energy Spectroscopic Instrument, operating in Arizona, is the largest spectroscopic survey ever attempted. By the time its 5-year mission concludes, it will have mapped the positions and velocities of nearly 50 million galaxies across cosmic history. Its baryon acoustic oscillation measurements already show a mild signal suggesting dark energy is evolving rather than constant. As the dataset grows, that signal will either strengthen into a discovery or fade into noise. Either outcome will reshape cosmology. The Euclid Space Telescope, launched by the European Space Agency in 2023, is mapping the large-scale structure of the universe across billions of galaxies. It will measure the distribution of cosmic matter and the gravitational lensing of background light with a precision that tests both dark matter models and alternative gravity theories. If modified Newtonian dynamics leaves a detectable signature in the pattern of galaxy clustering, Euclid will find it or definitively rule it out. On the ground, a new generation of cosmic microwave background experiments is taking shape. CMB S4, a collaboration of universities and national laboratories across the United States, will map the microwave sky with 10 times the sensitivity of the Planck satellite. It will resolve the finest angular scales, search for the primordial gravitational wave signal from cosmic inflation, and test the circular anomaly predictions of Roger Penrose's conformal cyclic cosmology. If the Hawking rings Penrose claims to see in existing data are real, CMB S4 will confirm them definitively. If they are statistical noise, CMB S4 will eliminate them. JWST itself is still looking deeper. Confirmed galaxies at redshift 14 are the current frontier, but the instrument is capable of detecting objects at redshift 15, 16, 20 if they are sufficiently bright. Each detection at higher redshift constrains the expansion history differently. Each spectroscopically confirmed oxygen emission line at extreme distance is another data point the standard model must account for. And then there is the Nancy Grace Roman Space Telescope, scheduled for launch later in this decade. It will survey an area of sky more than 200 times larger than JWST's field of view, finding rare objects that JWST's narrower gaze could never encounter. Its supernova survey will test the dark energy equation of state with unprecedented statistical power, directly addressing the question raised by the Yonsei University team, whether cosmic acceleration is genuinely slowing down. These instruments are not working in isolation. They are a coordinated pressure test on the most fundamental questions in science. Each one probes a different pillar of the standard model. Together, they will distinguish between a model that needs astrophysical patches and one that needs to be replaced entirely. Within a decade, the observational case will be decided. Some of the tensions JWST has opened will be resolved. Others may deepen into certainties that cannot be dismissed. We are not waiting for a revolution. We are living inside one. And the implications of what we find will reach far beyond telescopes and equations, because the age of the universe turns out to matter for everything, including the question of whether anything else in this vast cosmos ever looked up and wondered the same thing we do. Imagine giving the universe twice as much time to work with. In the standard model, the first stars ignited roughly 200 million years after the Big Bang, forged from pure hydrogen and helium in clouds so cold and dense that gravity finally won. These were the population 3 stars, the progenitors of everything. They were massive, short-lived, and explosive. When they died, they scattered the first heavy elements into the surrounding gas. From those enriched clouds, the second generation of stars formed. From those, the third. The oxygen we breathe, the calcium in our bones, the iron in our blood, the silicon in every processor ever built, All of it was manufactured in stellar cores and distributed by stellar death. In a 13.8 billion year universe, this entire chain had to begin and accelerate with extraordinary haste. The oxygen detected in JADESGSZ140, seen less than 300 million years after the Big Bang, demanded multiple stellar generations in what the standard model allows as barely enough time for one. The timeline was compressed almost to the point of impossibility. Now give the universe 26 billion years. In Rajendra Gupta's expanded timeline, the galaxy at redshift 14 is not 290 million years old. It exists in a universe that is approximately 3.5 billion years old. 3.5 billion years is enough time for population 3 stars to form in abundance, live their violent lives, and seed the cosmos with oxygen. It is enough time for a second generation to do the same. It is enough time for what JWST observes to be the product of a deep and layered stellar history that we simply never had the instruments to reach before now. The implications cascade outward. In an older universe, the cosmic web of filaments and voids that organizes matter on the largest scales would have had more time to grow from its earliest seeds. The structures we observe today, the chains of galaxy clusters connected by vast threads of gas and dark matter stretching hundreds of millions of light years, would reflect a longer history of gravitational assembly. The giant arc discovered in 2021, stretching more than 3 billion light years across the sky and seemingly too large to exist under the standard model, would be less anomalous. The Big Ring, another enormous structure found in 2024, would have had time to form by ordinary gravitational processes. Stars themselves would look different in their statistics. The fraction of old, metal-poor stars in our own galaxy, those that carry the memory of the earliest chapters of cosmic history, would represent a longer story than we currently assign to them. The Methuselah star, the ancient object sitting in the Milky Way with an age measured near 14 billion years, would no longer press uncomfortably against the edge of the universe's supposed timeline. It would simply be old, and old would be fine. An older universe is a more generous one. It is a universe where the laws of physics did not have to be bent to allow what JWST observes, where the impossible becomes ordinary, where the chemical richness of the cosmos is the expected product of time rather than a violation of it. But time itself is not the whole story, because this expanded history has consequences that reach all the way down to the world we live on, and to the question that may matter more than any other we have ever asked. The age of the universe is not an abstract number. It is the foundation of every question we have ever asked about whether we are alone. In the standard model, the universe is 13.8 billion years old. Our star is 4.6 billion years old. Complex multicellular life appeared on this planet roughly 600 million years ago. Technological civilization has existed for perhaps 10,000 years. All of that history is compressed into the final third of cosmic time. The universe spent 9 billion years just getting the conditions ready for our star to form. Now double the universe's age. In a 26 billion year universe, the last 13 billion years look exactly the same. Our star still forms when it does. Earth still condenses from the same cloud of gas and dust. Life still takes the same path on this world. Nothing in our local history changes. What changes dramatically is everything that happened in the first half of the universe's existence. The half the standard model effectively erases. In a universe with a 13 billion year head start, stars formed, planets coalesced, and the conditions for complex chemistry developed in systems that predate our solar system by enormous margins. The conditions that allowed life to emerge here took roughly 4 billion years of stellar and planetary preparation. If the universe is 26 billion years old, those conditions could have been met in other systems, 2, 3, even 5 billion years before our planet existed. This transforms the Fermi paradox. The The Fermi paradox is the tension between the apparent likelihood of life elsewhere and the complete silence we observe. In a standard model universe, the oldest rocky planets capable of supporting complex life might have formed only a few billion years before Earth. The lead time is short. Perhaps we are among the earliest. Perhaps the silence is simply youth. In a doubled universe, the silence becomes genuinely strange. If the conditions for complex life existed 10 billion years before our planet formed, and if those conditions are anywhere near as common as planetary surveys suggest, then something profound must explain why we detect nothing. Either life remains vanishingly rare, regardless of available time, or something in the universe systematically prevents technological civilizations from persisting long enough to be heard, or we are looking with the wrong instruments in the wrong directions. The anthropic implications are equally striking. We exist at a particular moment in cosmic time. We evolved on a planet enriched by multiple generations of stellar death. We depend on carbon, nitrogen, and oxygen, all products of those generations. In the standard model, this enrichment had to happen quickly. In an older universe, it happened gradually, with time to spare. If the coupling constants of nature have been slowly changing since the beginning, as Gupta proposes, then the physical laws that allow biology to function may represent a specific window in cosmic history, a window that opened after billions of years of preparation and may eventually close as the constants continue to drift. We are not the center of the universe. We have known that for centuries, but we may be the product of a precise and particular moment in its evolution, one that took far longer to arrive than we ever imagined. The universe spent more time preparing for what came to be than the textbooks gave it credit for, and perhaps, if we are honest, that debt of recognition was always owed. There is a pattern in the history of science that appears again and again, so reliably that it almost qualifies as a natural law. We measure something. We are confident we have measured it correctly. We are wrong. The correction comes from a new instrument, a new method, or an inconvenient observation that refuses to disappear no matter how many times it is checked. And each time, the revised number is more surprising than the one it replaced. For most of recorded history, the Earth was thought to be a few thousand years old. The calculation came from the best available evidence of the time. Those who made it were not unintelligent. They were working within the limits of their tools and their data. By the 19th century, geology had expanded that estimate to hundreds of millions of years. The evidence of rock layers, erosion rates, and sediment deposition made a young Earth untenable. Scientists adjusted. Some resisted. The consensus eventually moved. In the 20th century, radiometric dating established Earth's age at 4.5 billion years and placed the age of the universe itself in the billions. That number has been refined repeatedly. The universe was first estimated at 2 billion years, then expanded to 10, then to 13.8. Each revision was resisted. Each became the new consensus. And each time, the people holding the current number spoke with a confidence that retrospect would quietly undermine. This is not a criticism of science. It is a description of science. The process of revision is the point. An enterprise that never updates its answers is faith, not inquiry. Science is distinguished precisely by its willingness to abandon comfortable numbers when better instruments demand it. JWST is such an instrument. It was built to see the cosmic dawn. It looked where the standard model said little of interest should be, and it found galaxies that should not exist. The tension between what the model predicts and what the telescope observes is real. The question is whether that tension belongs to the astrophysics of how those galaxies formed, or to the cosmological timeline within which they had to form. That question has not been answered. Scientists are working on it with the best tools their generation has ever had. Some will prove right. Others will look, years from now, like the geologists who spent decades insisting the continents could not have moved. The lesson is calibrated confidence. We should believe the evidence we have. We should hold that belief firmly enough to act on it and publish on it and build instruments to test it. We should not hold it so completely that we stop looking for the evidence we do not yet have. The cosmic microwave background is genuinely extraordinary evidence for the standard model. So are the spectroscopically confirmed galaxies at redshift 14 and the oxygen in a system that, by the standard timeline, had no business containing it. Both things are true simultaneously. Both demand explanation. The universe does not care about our preferred timelines. It was old before we existed. It has been rearranging itself since before anything alive existed to watch. Our measurements are new. Our certainty is borrowed. The next chapter of this story has not been written yet. The telescope is still looking, and what it finds next may change everything one more time. There is a galaxy at redshift 14.32. It sits in a small patch of sky in the constellation Fornax, a region so unremarkable that astronomers chose it precisely because there was nothing obviously special there. JWST stared at that patch for hundreds of hours, collecting photons that had been traveling since before our solar system existed, before the first stars in our galaxy ignited, before anything we would recognize as our universe had taken its current shape. The light that built the image of that galaxy left its source when the cosmos was less than 300 million years old by the standard accounting. It crossed 13.5 billion light-years of expanding space to arrive in a mirror made of beryllium and gold, folded into the shadow of a sunshield the size of a tennis court, drifting 1 million miles from the only planet known to host the beings who built it. That galaxy should not exist as we have found it. It is too massive, too luminous, too chemically enriched. It contains oxygen, which requires generations of stars to manufacture and scatter across space. It contains dust, which requires those generations to have completed their full cycles of birth and death. The standard model of cosmology, the one constructed over a century of brilliant and meticulous science, says there was no time for any of this. Less than 300 million years after the beginning of everything, a system of 400 million stellar masses simply should not have finished so much living, and yet it is there. We do not yet know what this means. That sentence is important to say clearly. Science lives in the gap between what we observe and what we understand. The honest answer to the question of how old the universe is, after everything this story has covered, remains genuinely open. 13.8 billion years is the number derived from the cosmic microwave background, backed by decades of precision measurement and 35 confirmed acoustic peaks. 26.7 billion years is what Rajendra Gupta derives from a framework where the forces of nature have been slowly fading since the beginning. An eternal age, cycling without beginning or end, is what Roger Penrose's mathematics suggests is possible. These are different answers to the same question, and they cannot all be right. But the question is alive again. That matters more than any specific number. For a generation, the textbooks agreed. The satellites confirmed. The physicists moved on to other problems. The age of the universe was settled, filed, and footnoted. JWST reopened the file, not because anyone told it to, because the universe contained galaxies that the file had failed to account for, and a telescope cold enough and precise enough to capture their ancient light could not look away from what it found. This is what science does at its best. It builds the most precise instruments it can. It points them at the most extreme places it can reach, and it listens to what comes back, even when the answer is inconvenient, even when it means the next generation will memorize a different number than the one we were taught. The universe is older than we thought. How much older, we do not yet know. The revised number may arrive within a decade, carried in the spectra of galaxies we have not yet confirmed, in the subtle evolution of dark energy signals accumulating in databases around the world, in the faint circular rings that may or may not be echoes of a universe that burned and reformed before ours began. It will come from the same process that gave us every number before it: careful observation, honest calculation, and the willingness to be wrong. We have always been measuring a moving target. The universe keeps growing older as we watch. Our instruments keep improving, Our models keep meeting their limits, and each time they do, we learn something that would have been unimaginable to the generation before. JWST is still out there, 1 million miles from Earth, drifting in the cold and the dark, still looking deeper into the past than anything humanity has ever built. It will keep sending data home. Each new image will be a test. Each confirmed spectrum will be a verdict on a theory. The search continues, and somewhere in the deep, at a redshift we have not yet reached, the universe is still keeping its oldest secrets.